Okay, I have your homework problems. The last set's up here. You can grab them. You're going to want to check them against the answer key because I just quickly perused them to make sure that you had done most of them. You don't know when I'm going to do that and when I'm going to grade them explicitly, so you want to continue. You want to not guess because you'll guess wrong. So they're there, and the answer keys are in the folders. Right below it, there's probably a narrated answer key for each one. Okay. And then you can turn in your take-home quiz problems at the end, Vinny. About one of what? The homework problems? Sure, go ahead.
It's quick.
Okay, tell me what number 4 is.
So it's a benzene.
Yes.
And
making carboxylic acid. So, what's the mechanism of this reaction? Somebody else asked that. So the OH minus is going to come in and deprotonate that, like so. And then what's going to happen is your C double bond O is over here. This pair of electrons moves down, and then that pair of electrons from the benzene ring then goes out and attacks the carbonyl, and then one of the CO double bonds goes to the O to make an O minus. It's like a Grignard reacting with CO2. And when you end up with, what you'll end up with is then an O double bond, the H here, a C double bond O with an O minus. And then your double bonds in the ring will look like that. Okay. Now, I suppose we could continue on to have I suppose we could have the pair of electrons move down here, and then have this pair of electrons move here, and then have that one move out to form the C, to react with the C double bond O. And you would end up forming that product. I think the difficulty here is, either way, this pair of electrons is going to move back, that pair of electrons is going to move up, because we're going to reform the carbonyl, or reform the aromatic ring. I'm going to end up with an O minus. Actually, I'm not. I'm going to end up with an OH. So when this pair of electrons moves here, and this double bond moves there, it's going to pick up that hydrogen. So that's a tautomerization step, is really what that looks like. So that is going to then form the OH. I'm going to end up with a C double bond O minus, and then the reason that there's a then H plus step in here is because at the end I need to protonate the carboxylic acid. This solution would be basic, and the carboxylic acid would be a base, would be in its deprotonated form under basic conditions. So I need to add the OH back into that. Down here I'd end up with the same sort of mechanism, except here I would end up with an OH and then my C double bond O, OH down here. My guess here as to why you only get one product and not the other is probably going to be because this product over here is going to have the ability to form that hydrogen bond, which would make that product overall more stable than the one down here. And so if we're looking at that, and we're doing this reaction under probably what would be considered thermodynamic conditions, because I'm not doing this at low temperature, then most likely I'm going to get the lowest product. There's a couple ways you could look at it. You could say, okay, is the C minus here or the C minus here going to have, which one of those two is going to have a greater negative charge? I don't know. I think the products is what drives this, but I don't know the exact answer to the question, other than that's what we get. So that would be the full-blown mechanism for that reaction. And the advantage of this is you take a phenol and you basically convert that phenol into what is now salicylic acid. And so being able to do that, the only other source of salicylic acid that's probably popular would be to go and rip off the bark of a bunch of birch trees. Because if you chew on birch tree bark, that has a lot of salicylic acid in it. It'll still, clear up your headache. It'll, take the intestine of the lining of your stomach and destroy it after a long time. Which is why we take the salicylic acid and we convert this OH into an acetyl group with a C double bond O, with a CH3 on the other side. And that's a little softer on the stomach. So the only thing I can think of is that it must be a more stable product, and then you have that, lowering of. If you have the same transition state for both, well, you wouldn't the transition state energy would come down a little bit because of the stability of the product. But that's a good point. Nobody's ever asked me that. Sarah?
So for that product you do in the top right corner, why do you have the hydrogen next to the O as well as
because I'm showing the hydrogen bond. So my answer is I think this is definitely a more stable product than this one because it can form that intermolecular hydrogen bond, and that will stabilize it.
Okay, so it's not like a separate alcohol.
No. And it really shouldn't be it should be a dotted line here, right, for the hydrogen bond. So that's what I'm saying. I think that intermolecular hydrogen bonds is what is causing the molecule to be more stable, and that's why we're forming this and not this one.
Okay.
Because I guess sterics would predict the other one, but that's not what happens. Okay. What other questions do you have?
About the single or about any of them?
I don't care. I'm open for questions. Any questions you want?
through
Breeze through.
the pre-lecture today.
Breeze through.
Yeah,
Well, I can put it on.
Over the points that you want to
That we want to know about. Okay. I can put it on.
do 53 minutes, so it's all 53 minutes pertinent to.
Well, all 53 minutes is always pertinent. Right? If it's not important, I'm not going to say it. I mean, you may not think so, but, you know, I think I'm the judge of that. Right? Because when I'm saying it, I'm deciding what's important and what's not important.
Okay, well, what should you have absolutely taken?
What should you take away from this? Here's the reason that we're putting aldehydes and ketones together. Well, I should ask you this, right? I should have you pull out a piece of paper and write this down and then collect it up at the end. But why am I grouping aldehydes and ketones together, and then I'm grouping carboxylic acids and all of their derivatives in another group? Why is there just a chapter on aldehydes and ketones, and then there's another chapter on carboxylic acids and derivatives? What's the difference between these two sets of molecules? Reem?
Aldehydes and ketones, the H and the R don't leave.
Okay, so in this case, I have two groups that don't leave. And?
Carboxylic acids, the OH can leave, or the Y group.
Okay, that can leave, and the Y groups can leave too, right? Okay, so that's a difference between the molecules. And so what does that mean? Let me take a nucleophile. I'm going to just do a generic. I'm going to take a negatively charged nucleophile. I'm going to react it with an aldehyde or a ketone. Tell me the first step of the mechanism. Oh, wait. This is pretty, everybody should know this, so we should keep everybody on their toes. Alyssa, what's the first step in the mechanism? What attacks carbon? Okay, nucleophile attacks the carbon and pair of electrons goes up here. Okay. There's the first step. Let's do the first step in the bottom set. We'll make that just a generic Y group. Okay, what's the mechanism for the first step here? You're all waiting for me to push the button. Okay, I'll push the button. Marissa?
Nucleophile,
And?
Y would leave.
Was Galai going to leave yet?
Oh, not yet. Same thing.
Exactly. So you could have said same first step. So we have the same first step in both of these reactions. Okay. So that's common for both. Now, what should I do next in the top reaction, Sarah? What should I do with this molecule right here? Next step. Well, should I add a hydrogen or what's
You want to make the minus active group of the bond.
okay, carbonyl wants to reform. Well, it can only do that if what? What's the only time that the carbonyl can reform in this case?
How many groups do they have?
If something can leave. And so in the molecule, the way I've written it, what can leave? The nucleophile could leave. Okay, everybody with us so far? So we want to reform the carbonyl. The only group that could leave is the nucleophile if it's a leaving group. I wouldn't even say good leaving group. If it's a leaving group, it can leave. What about hydrogen and carbon? They are not leaving groups because they never leave. So, best case scenario for the carbonyl is this happens, which does what? Puts us in an equilibrium. Now, if the carbonyl can't reform, that means the nucleophile was either C- or H-. We already did that, right? When we did Grignard's and lithium aluminum hydride, sodium borohydride reductions. So we already did that. So now what we're talking about is adding aldehydes, adding to aldehydes and ketones, new nucleophiles. Before it was just R- or R-, C- or H-. Down in the bottom case, what could leave? Y could leave, or the nucleophile could leave. So which one's going to leave? Depends on what? Well, which one's going to leave? Nucleophile or Y? If Y is what? If it's a better leaving group. Right? So now we're kind of in a position here where if the Y's better leaving group than the nucleophile, it will then leave and we'll end up doing what we call substitution. We'll end up with the nucleophile in the Y position. But what if the nucleophile is a better leaving group? Then we go backwards. So it's really all about us knowing which groups are the best leaving groups, and we're going to have to know those in order, sadly. Right, we're going to have no choice but to rank those, which I probably have already done when we talked about all the different kinds of carboxylic acid derivatives that we're going to look at. Okay? But that's the next couple chapters. Where we're at right now is the top part. So, what do I want you to take away? I want you to take away that basically this right here, without going backwards, if I then sit here like so, and then I add my H+, then If I can't reform, then I'm going to form that. But these cases were Grignards and H minus, and we've already done that. So the reaction, the equilibrium reaction I wrote in the box, covers every single reaction that was in 53 minutes of lecture. Right? So if you got this under control, you're good. Well, sort of. Because there were some extra steps in there along the way. So if I had to sum up the whole 53 minutes, it would be that. But remember, that's just the summary. That's the Cliff Notes. Right? The Cliff Notes will get you through the quiz. It won't get you through the exam. You need more than that. You need to read the book to get through the exam. All right, let's take... Let's do that reaction. And the reactions of aldehydes and ketones are, for the most part, the same. Although, let me ask this question to someone. Which is more stable, aldehyde or ketone? Ketone, because it's more substituted. All right, so I could react this aldehyde to this ketone with water. Can I do it this way? No? What do I need? I need acid as a catalyst. Why do I need acid as a catalyst? Because water is a neutral nucleophile, and actually, I don't think I added any negatively charged nucleophiles to the aldehydes and ketones. And there's a reason for that, but that's like 3 chapters ahead. So we'll get there. All right, so what's the product of this reaction going to be, the top one? Write it down. What if you're like, oh, I can't remember what the product is? Then you're stuck. So what should we do if you're stuck and you haven't memorized that yet? Sorry, learned that yet. First step in the mechanism. What's the first step in this mechanism? Protonate the carbonyl oxygen. Which way does the arrow go? O to H or H to O?
O to H.
O to H? Remember that for the next exam. Okay, so now I've got my double bond with my O with my H positively charged. What happens next? Water comes in, or does this structure have a resonance structure? If I take this pair of electrons and move it to the oxygen, because I'm missing a lone pair, then what? I get 2 resonance structures. Now, it doesn't matter which one of these 2 resonance structures you use. I could have water attack either one. If the water attacks the one on the left, what happens? Then the pair of electrons has to go up to the oxygen. So if I do that, what am I going to get? A C with an OH on it, an H, and then down here, the oxonium ion. Again, same two steps. And then what happens? Vinny, what happens next? Down here. Could, but then I'd be going backwards. I want to go forwards. Final step. Okay, which way does the arrow go? Bond to oxygen or oxygen to bond to oxygen or bond to hydrogen? Bond to oxygen. Remember that for the next test. That's probably the most common error in reversing arrows that I see. Okay, so then that happens. So I lose my H+, which I should because H+ was the catalyst to begin with. So I get two OHs stuck to this carbon. That is called a hydrate. That is your hydrate. Is it stable? Not this one. So where does the equilibrium lie? Towards the hydrate or towards the aldehyde? Aldehyde. So with a couple of additional steps, because I had to have acid in order to do this reaction, I pretty much just did the first step. I pretty much did this mechanism. Except in that case, the O- kind of just sits there and gets protonated. Now if I gave you a hydrate and said add acid to it and water to go back to the aldehyde, could you do that mechanism? Well, if you can do it forwards, you should be able to do it backwards. So take this mechanism right here and do it backwards, and you've got the mechanism to form the aldehyde from the hydrate. You might say, is that relevant? Have we done that before? No. This is the first time we did it. But, well, I'll leave the, we'll do that later. Okay. So what would the mechanism be if I decided to do this with an alcohol? If I said, you know what, I'm going to take my aldehyde and now I'm going to add methanol to it with acid as the catalyst. Could you do that mechanism? Well, if you can do the one with water, HOH, you can do the one with ROH, because it's the same. So what's this product going to look like? I'm going to have an R attached to the C attached to the H, and what's attached to the carbon that was the carbonyl carbon? What two things are going to be attached to that carbon? An OH and an OCH3. And that is called that is a hemiacetal. Because it's hemi because it's half of an acetal. It's an acetal because when you locate the carbon that is attached to the two oxygens, it has a carbon and an H, which means with the carbon and the H, it came from an aldehyde. If there was two R groups there, it would be called a hemiketal. So those are your choices, acetal, ketal, whether it came from an aldehyde or a ketone. And this again should be an equilibrium reaction, and over here there should be water. So making acetals, making hemiacetals, making hydrates is kind of difficult because the equilibrium for these favors the starting aldehyde or ketone, except in a couple of cases. And our biggest case will be if it forms a cyclic compound. Then the equilibrium would favor the right hand, would favor the product. And if you have some really strange aldehydes like formaldehyde, if you put formaldehyde in water, it makes the formalin, which is the hydrate, that's stable. And if you put electron withdrawing groups over on this carbon, then that stabilizes the product as well. Actually, it doesn't stabilize the product. It destabilizes the reactant and makes the equilibrium shift to the right. So 3 chlorines and you've got like chloral hydrate. Okay. But if you're at a hemiacetal, what can happen next? I still have acid present. So what's the acid do? Protonate the oxygen. And in this case, which one? The OH? The OH is going to take me forward, right? The OCH3 is going to take me back to the beginning. So I should probably keep going. So I'm going to go ahead and protonate the OH. And then I'm going to get an oxonium ion. And then what happens next? Water leaves. I know, I agree, it's pretty boring. For those that yawned. It's boring. We've done this over and over again. It's just now we're putting all the steps together to do something else. Okay, I've got that. So what happens now? Well, if I started with like excess alcohol, or if I started with 2 equivalents of alcohol, the alcohol is going to come in and it's going to do what? Attack the carbocation. Now I'm going to end up with a COH with a CH3OH. Down here I've got an OCH3, got a plus charge on that oxygen, an H over there, and then in the final step I do what? I'm going to lose H plus, right? But every one of these steps is reversible, so I could start with in this case, an acetal, and react with acid and reverse the whole process to get me back to an aldehyde. Okay. So I guess another thing that I would have hoped you would have taken away from the 53 minutes of lecture is there's really not a whole lot of new stuff here. It's really just the same thing over and over again with different molecules. Right? First step can be done with water or alcohol. The second, adding a second alcohol, must be done with another alcohol. So I can make aldehydes, I can make acetals and ketals now. Brian?
So when you protonate the alcohol to form the hydronyl ion and then it leaves, what's preventing another mi-ketal from coming in and adding to it? So having the
Oh, you want to take like this and add it to the carbon? You said another hemi-ketal.
yeah, I was thinking the OCH3, but then that would make the oxygen unstable. Or
So once that leaves and you get over here, you would have a competition between water and CH3OH. If water adds to it, you just go backwards. Right? So the overall reaction here is this. Aldehyde plus 2 alcohols with acid as the catalyst, so it's over the arrow, would make would make the acetal plus a water. In the lab, in order to make the acetal, I got two choices. I either use an excess alcohol to push the equilibrium to the right by Le Chatelier's principle, or I remove the water as it's formed, which pushes the equilibrium to the right. And actually, most of the time, we would probably remove the water. And the way we would remove the water would be, we would probably reflux this, and we'd have a special apparatus in between, so that as the water and the alcohol and the excess alcohol distilled into the reflux condenser, we'd have something in between so that when it dripped back down, it would be going through a drying reagent. Not the stuff you use in, well, not the calcium chloride pellets or anything like that, but maybe something a little more sophisticated. And so as the water evaporates and then drips down, it would be removed, so that eventually we would make nothing but the acetal. Right? And as long as we remove the water, then the acid isn't really going to do all that much. But again, the equilibrium for this lies over here. The best way to push the equilibrium to the right is to make this cyclic. Is to make the cyclic acetal.
So is there water in our final product?
Well, what I did was I lost the water. I should have said up here I lost the water. So in the overall equation, you would show water on the right-hand side, but in the mechanism, I just lost the water in that step.
So if you didn't have the alcohol, it would like have an intramolecular reaction, become cyclic?
Not this one. This one isn't going to go cyclic. In order to make this cyclic, what I need is this. I need one molecule with two OHs on it. So that way the first OH adds, and that's like down here, and then when the water leaves, the other OH can wrap around and add to the carbon and make a cyclic product. So I need a dialcohol. And I think in the video, the one that's most commonly used to react with is this one, which is ethylene glycol. That's the one that's used to make the stable cyclic acetals and cyclic ketals, is the 2-carbon dialcohol. So this is ethylene glycol. And so ethylene glycol is dirt cheap. There's tons of it around because it's used in your car radiator to lower the freezing point of the water, so that unless it's like really like probably minus 40 or something like that, your radiator block doesn't freeze. Because if that happens, water expands and you're buying a new radiator block. And your car just doesn't. In the summertime, ethylene glycol lowers or raises the boiling point of the water in it, so that way your engine can dissipate the energy into that. So that's one use of ethylene glycol. The other use of ethylene glycol, honestly, is this reaction to form those types of cyclic acetals or cyclic ketals. Because when you form the cyclic product, it pushes the equilibrium to the right. And the reason for making these is that they are stable. Okay. And then you would have a water molecule over here. You could do this, but I don't think anybody synthetically does this, because the ethylene glycol is a commercial product. Did I say in the video it kills pets? Yes, no. No, I didn't. So what happens is, what happens is if you have your antifreeze, if you're filling up your antifreeze, you want to make sure you don't spill any in the driveway or probably in the garage, because this ethylene glycol has a very sweet taste to animals, probably to humans, but we might not know. Hopefully we know better than to just start licking it off the basement floor. But small pets, large pets, wild animals will come in and they will lick this up, and then it acts as a poison. So they did make a more environmentally friendly antifreeze, which is this one called propylene glycol. And various forms of propylene glycol are in all sorts of things like makeups and shampoos and consumer products. Every so often I see an article that it's like cancer causing and will kill you, but if that's the case, there should certainly be more of that going on, because it's in a lot of things. And that's not a reason why it shouldn't happen. It's just that's sort of the statistics on it. But the propylene glycol they use, you can buy environmentally friendly antifreeze. The only problem is you have the little tester that you stick in and you pull it up, and there's little balls that float depending on whether it's too concentrated or not. That doesn't work, so you got to buy another one. I personally, that's what we have mechanics for. That's what I have a mechanic for. It's just they can do that kind of stuff, because I don't have a garage and I don't have you can only do so much in the parking lot outside of like whatever your favorite Napa store or whatever there is. They should just put a jack in those parking lots, because everybody does their maintenance outside of that. But I think there's probably be liability issues and other things. But they're 1 carbon. When somebody says, hey, what difference does a carbon make? Or when you put an additional carbon or take away a carbon on the exams, in this case, 1 carbon's pretty important. Of course, you already kind of knew that, because we don't go around drinking methanol, because you go blind or die. Whereas ethanol, well, you could die. You could do lots of stupid things, but short of death. But at least in the same concentration ranges, it's not going to kill you the way methanol will. So one carbon makes a huge difference. And you might say, well, what would the product of that reaction be? It would just be a carbon or a ring now with 1, 2, 3 carbons in it. Or not 1, 2, 3 carbons in it. So this would actually be a 1, 2, 3, 4, 5, 6 member ring. But I don't know that synthetic chemists who do these kinds of reactions have gone to the more environmentally friendly compound because they're not using it in tons. Now the real reason for making these cyclics is that aldehyde is protected. So that's an aldehyde right now, but it's sitting as a acetal. I can do anything to any part of this molecule as long as, and this thing will stay intact, as long as I don't use acid and water. So I think the example that was in the notes was I've got another part of the molecule that I want to make a Grignard out of. And if I made the Grignard with the aldehyde present, the Grignard at this end of the molecule is going to react with the aldehyde at this end, and I'm not going to get what I want. If this is protected, if the aldehyde is protected, the Grignard is fine. The Grignard reacts with something else. When I'm done, I add my acid and my water. My protection goes all the way back to aldehyde, and I just protonate my Grignard product. So these kinds of reactions are called protections, and they're done all the time in real synthesis to keep my aldehydes and ketones intact. So usually at this point what I do is I say, we need a take-home quiz. You may not agree with that, but go out and get a PhD and then you can teach this class. Well, get a PhD, get this job. Then you can teach this class. So here's your take-home quiz. I'd like you to draw the mechanism for this reaction. So react both OHs with the acid catalyst. Show me all the steps. You do not have to show me transition states. Just show me the steps and make that cyclic acetal product. Just so that we all have the mechanisms in place. Then I would also normally say, oh, we need to have an in-class quiz on Wednesday. Right? On the reactions that were in this 53-minute video, which are all pretty much the same, but just writing the products of them. So I think we'll do that too. But don't worry, after Wednesday, you're done for a couple of days. And when we come back, remember that when we come back, Tuesday's not Tuesday. I don't know what day it is, but it's a day we have class. It's Monday, I think. So we'll have class on Monday and then Wednesday, and I think the exam is that Friday. Okay, so take your homework problems, leave me yours, and
So, this doesn't work unless you have liquid ammonia?
no, it will.
Isn't this one?
You got